Assalamu alaikum. Welcome to this course called Chemistry 112. It is a mixture of organic and biochemistry, about 40 to 60%. And we want to start with the organic part, chapter 12, entitled Introduction to Organic Chemistry Alkanes. We will cover the following topics in this chapter from 1 to 10. We begin with organic chemistry, is the study of carbon compounds, and as you studied in general chemistry, carbon is found in group 4 in the periodic table. It is a tetravalent. It always forms 4 bonds, which means it does not violate the octet rule. Carbon must have 4 bonds around it. Organic molecules have covalent bonds. And this is an example of a simple organic compound called ethane. 2 carbons and 6 hydrogens. Notice that the 2 carbons are joined together by a single bond. Now, if we look at the carbon atom and the 4 groups that surround the carbon. Now, when carbon bonds to a more electronegative atom, such as Cl, a polar covalent bond results. So, for example, chloromethane is polar, as you can see. This is the direction of the polarity, from positive end to negative end. Whereas methane itself is non-polar. Now, organic molecules have specific 3-dimensional shapes. These are other organic compounds, and we will study them. Namely, ethylene as an example on alkenes, and acetylene or ethane as an example of alkyne. Organic molecules often contain nitrogen and oxygen in addition to carbon and hydrogen. Nitrogen, as it's known, it can form single, double, and triple bonds to carbon, and also to itself. Oxygen can form single and double bonds, whereas hydrogen can only form single bonds to a carbon. Now, covalent bonding. Individual molecules separate, lower melting and boiling points than inorganic salts, of course. Many organic compounds are liquids or low melting solids at room temperature, and a few are gases. Most organic compounds are insoluble in water. There is a rule in chemistry, like dissolve like, which means that polar dissolve in polar and non-polar dissolve in non-polar. So, organic compound are non-polar and water polar, so they cannot be mixed with each other. Almost all of those that are soluble do not conduct electricity. Only small polar organic molecules or large molecules with many polar groups interact with water molecules and thus dissolve in water. Now, lack of water solubility for organic compounds has important consequences. For example, the interior of a living cell is a water solution that contains many hundreds of different compounds. Cells use membranes composed of water-insoluble organic molecules to enclose their interiors and to regulate the flow of substances across the cell boundary. And usually these non-polar groups are buried inside the cell. Organic compounds can be classified into families according to structural features. The chemical behavior of family members is often predictable based on their specific grouping of atoms. There are a few general families of organic compounds whose chemistry falls into simple patterns. So we have millions of organic compounds. So instead of studying all of these, we study groups of families. Each family or a group has a certain functional group, as we will see, which characterizes that family or that group. The structural features that allow classification of organic compounds into families are called functional groups. Okay, so what is a functional group? Is an atom or a group of atoms within a molecule that has a characteristic physical and chemical behavior. And we will see this as we go. Each functional group is part of a larger molecule, and the molecule may have more than one functional group present. A given functional group tends to undergo the same reactions in every molecule that contains it. They have similar reactions. The chemistry of an organic molecule is mainly determined by the functional groups it contains, not by the size or the complexity of the molecule. Now, if we look at this table, 12.1, some important families of organic molecules. We started with alkane, chapter 12, then we will move to other families. So here, in this column, you have the family name, functional group structure, simple example, line structure, and name ending. Each family has a name ending. Alkane ends with an "ane", and this is an example, 3 carbon propane. And always alkane contains single carbon hydrogen and single carbon-carbon bonds. Propane can be represented by this line structure. Alkene, double bond, example ethylene, it ends with "ene". Alkyne, like acetylene or ethane, ends with "ine". Aromatic, there is no name ending, like benzene. Alkyl halides, ethyl chloride is an example, also non-name ending. Alcohol, like ethanol, it ends with OL, OL. The ether, O, bonded to two carbons, or to two methyl groups. This is called diethyl ether or simply ethyl ether, and there is no name ending. Amine, like ethylamine, it ends with an amine, the family name. Aldehyde, like 2 carbon, this is the functional group. Ethanal, it ends with Al. Ketone, like acetone, it ends up with "-one". Then we have carboxylic acid, like acetic acid, it ends up with "-ic" acid. Anhydride, like acetic anhydride, there is no name ending. Ester, like methyl, this is methyl, and this part is acetate. The anion part of acetic acid. So we say methyl acetate. And the name ends with "ate". The amide, like acetamide, ends with an amide. Thiol, like ethyl thiol, there is no ending. Disulfide and disulfide, none. There is no ending for them. Now, the first 4 families are hydrocarbons, organic compounds that contain only carbon and hydrogen. Alkanes have only single bonds and contain no functional groups. Alkenes contain a carbon-carbon double bond functional group. Alkyne contain a carbon-carbon triple bond functional group. Aromatic compounds contain a 6-membered ring of carbon atoms with 3 alternating double bonds. Now, the next 4 families have functional groups that contain only single bonds and a carbon atom bonded to an electronegative atom. For example, alkyl halides have a carbon to halogen bond, alcohol a carbon to oxygen bond, ether two carbons bonded to the same oxygen. Amines have a carbon-nitrogen bond. Now the next 6 families contain a carbon-oxygen double bond. Aldehydes, ketones, carboxylic acid, anhydrides, ester, and amides. The remaining 3 families, they have functional groups that contain sulfur, thioalcohols, known simply as thiols, sulfides, and disulfides. These play an important role in protein function, as we would see in the second part of this course. Now, the general rule for all hydrocarbons except methane is that each carbon must be bonded to at least one other carbon. The carbon atoms bond together to form the backbone of the compound, with the hydrogens on the periphery. The general formula for alkanes is this: CnH2 HM plus 2, where N is a number of carbons in the compound. For example, if N equal 1, then H equal N must be 2. If it is 1, then it is CH3. This must be 2N plus 2. No, this is 2N plus 2. No, if it becomes 2, so we must fix this. The formula is CnH2N. We must put 2N plus 2, where N is the number of carbons. Because when N equal 1, 2 times 1, 2 plus 2, 4, this becomes CH4 methane, the simplest alkane. As larger numbers of carbons and hydrogens combine, the ability to form isomers arises. Compounds that have the same molecular formula but different structural formula are called isomers. There are 2 ways in which molecules that have the formula C4H10 can be formed. The 4 carbons are joined together to each other in a straight fashion, and the hydrogens on the periphery. This is called straight chain, or you could have a branched chain. You can move this methyl to carbon here, and you replace this hydrogen with methyl, and this H comes here. So this is called a branch point. So both compounds are isomers. So a straight chain alkane is an alkane that has all its carbons connected in a row. A branch chain alkane is an alkane that has a branching connection of carbons. Constitutional isomers are compounds with the same molecular formula but with different connections among their atoms, as we saw. These isomers of a given molecular formula are chemically distinct from one another. They have different structures and physical properties, of course, as we will see. When the molecular formula contains atoms other than carbon and hydrogen, the constitutional isomers obtained can also be called functional group isomers. There are isomers that differ in both molecular connection and family classification. For example, ethyl alcohol and dimethyl ether both have the formula C2H6O but have very different properties. So different atom connections and different functional groups. So these are called functional group isomers. Even ethyl alcohol and dimethyl ether, these two are known as functional group isomers, whereas the previous ones are called constitutional isomers. A condensed structure is a shortened way of drawing structures in which carbon-carbon and carbon-hydrogen bonds are understood rather than shown. This is the structural formula. This is the condensed formula. This is the structural formula, and this is the condensed formula. These two, the one we talked about, butane and 2-methylpropane, are constitutional isomers. This is the straight chain, this is the branched chain. So they have the same atom connectivities, but they are different compounds. They are called constitutional isomers, butane and isobutane. Occasionally, not all the CH2 groups, which are called methylenes, are shown. CH2 is shown once in parentheses with a subscript indicating the number of methylene units strung together. For example, we have here how many methylene groups we have: 1, 2, 3, 4. So we put between two brackets CH2 by 4. And this is CH3, the first one, and this is CH3, the last one. So this is the same as this. A line structure, however, or line angle structure, is a shortened way of drawing structures in which carbon and hydrogen atoms are omitted, are not shown. A carbon atom is understood to be whenever you have a line begins or a line ends at every intersection of two lines. It is found whenever a line begins or a line ends and at every intersection of two lines. This is carbon, 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 and this is the structure. And hydrogens are understood to be wherever they are needed to have each carbon form 4 bonds. So this is the line structure of this compound. As you can see, carbon atoms are omitted, hydrogens are omitted, and on each carbon then it must have 4 bonds. So you complete the octet with hydrogens. Drawing organic structures. Now, each carbon-carbon bond is represented by a line. Anywhere a line ends or begins, as well as any vertex where two lines meet, represents a carbon atom, as we saw. Any atom other than another carbon or a hydrogen attached must be shown. Since a neutral carbon atom forms 4 bonds, all bonds not shown for any carbon are understood to be the number of carbon-hydrogen bonds needed to have the carbon form 4 bonds, as I explained before. Every carbon atom in an alkane has its 4 bonds pointing toward the 4 corners of a tetrahedron. The 2 parts of a molecule joined by a carbon-carbon single bond in a non-cyclic structure are free to spin around the bond, giving rise to an infinite number of possible conformations. The various conformations of a molecule are called conformers. So when 2 carbons are connected with single bonds, then there is a free rotation about this single bond, and many possible conformations can be drawn. These various conformations are called conformers. At any given instant, most of the molecules have the least crowded, lowest energy extended conformation. As long as 2 structures have identical connections between atoms and are interconvertible, they are conformers. So here are examples. A, B, and C, all of them are called conformers of butane. Because we have single bonds here all the way, there is always a free rotation. So all of these are, because you can convert one to the other without breaking of the bond. There is no need to break the bond because it is a single bond. The system of naming or nomenclature was devised by the International Union of Pure and Applied Chemistry, the so-called IUPAC. In the IUPAC system for organic compounds, the chemical name has 3 parts: prefix, parent, and suffix. As you can see here, we have, this is your parent. Parent refers to how many carbons are there, and the prefix, where are substituents located, and the suffix, what family does the molecule belong to. So again, the prefix specifies the location of the functional groups and other substituents. The parent tells how many carbon atoms are present in the longest continuous carbon chain, and the suffix identifies to which family the molecule belongs. As we explained the various families we saw. Is it an aldehyde? Is it a ketone? Is it an alcohol? Is it an alkene, alkyne, etc., etc. Straight chain alkanes are named by counting the number of carbon atoms and adding the suffix, the family suffix "-ane". Straight chain alkanes have no substituents, so prefixes are not needed. Suppose you have 4 carbon alkane, 4 carbon butane. Butane, it does not have a prefix because there are no substituents. Even straight chain alkanes have no substituents, so prefixes are not needed. So it is butane. The ending "-ane" reflects the family. As we said, alkane, the end name is the suffix "-ane", "-ane". So butane, it ends with "-ane", so this is the name. You can have hexane, propane, butane, pentane, heptane, hexane, nonane, decane, etc. As we can see here. So, name of straight chain alkanes, we have here the simplest one with the number of carbons, 1 carbon methane, 2 carbon ethane, so on. So you must know these. From methane to decane, from number of carbons 1 to 10, you should know these. Okay, you should know this table, and you can apply the general formula here, CnH2n plus 2. You can apply the general formula here. Substituents such as CH3 with this dash and dash CH2, CH3, that branch of the main chain, are called alkyl groups. So this is called methyl group. This is called ethyl group. If you have additional carbon here, it's called propyl group. وهكذا. So how they are formed, these alkyl groups? You take the parent alkane like methane. You take the parent alkane methane and you remove 1 hydrogen. The one in red, you can move any one of these similarly. You have methyl group, you have the parent alkane ethane, you remove 1 of these 6 hydrogens to get an ethyl group. So if these are at a branch point, they will be named ethyl, methyl, etc., as we will see. The situation is more complex for larger alkanes. Some common alkyl groups, know these: methyl, ethyl, propyl, isopropyl. You see this small n, this stands for normal propyl. Why? Because there is another isomer called isopropyl. You see the difference, 3 carbons, no branching here. If the hydrogen is removed from this second carbon, it's called isopropyl. This group is called isopropyl. This is called N-propyl. Now if we go to 4 carbons, the normal one, N-butyl. If the substituent from this, if we remove the hydrogen from this carbon, it's called secondary butyl. If we remove the hydrogens from this carbon with this branch, then this is called isobutyl, same as this. You see the similarity between these two? Here you add to isopropyl CH2, it becomes isobutyl. You see the similarity? However, if you remove the hydrogen from the central carbon here, then this is called tertiary butyl. Notice that the red bond shows the connection to the rest of the molecule, of course. Now there are four possible substitution patterns for carbons attached to four atoms. Primary carbon atom is a carbon atom with one other carbon attached to it. If one carbon is attached to one carbon only, then this is classified as primary carbon for each one. The secondary carbon is a carbon atom with two other carbons attached to it. Now, a tertiary carbon atom is a carbon atom with three other carbons attached to it. A quaternary carbon atom is a carbon atom with four other carbons attached to it. To show you the example, here this is only one carbon. There is no classification. Whereas here, this carbon is attached to this carbon, or this carbon is attached to this. So both of them are primary. Now this is a primary. Now this in the middle attached between two carbons, this is secondary. However, this carbon is attached to 1, 2, 3. So this is called tertiary. This carbon is attached to 1, 2, 3, and here we have another fourth attachment. This is a quaternary. This is secondary. This is primary. This is a primary, and so on. Branch chain alkanes can be named by the following four steps. Name the main chain. Find the longest continuous chain of carbons and name the carbon according to the number of carbon atoms it contains, as we saw in that table. The longest chain may not be immediately obvious. Yes. Number the carbon atoms in the main chain, beginning at the end near the first branch point. Identify the branching substituents and number each according to its point of attachment to the main chain. Write the name as a single word, using hyphens to separate the numbers from the different prefixes and commas to separate numbers if necessary. If two or more different substituent groups are present, cite them in alphabetical order. If two or more identical substituents are present, use one of the prefixes di, tri, tetra, and so forth, but do not use these prefixes for alphabetical purposes. Now, what are some of the properties of alkanes? Alkanes contain only non-polar carbon-carbon and carbon-hydrogen bonds. The only intermolecular forces influencing them are weak London dispersion forces. The effect of these forces is shown in the irregularity with which the melting and boiling points of straight-chain alkanes increase with molecular size. Now, the first four alkanes, methane, ethane, propane, and butane, are gases at room temperature and pressure. Alkanes with 5 to 15 carbon atoms are liquids. Alkanes with 16 or more carbon atoms are generally low-melting, waxy solids. Note these. And this table or this figure shows you how the melting and boiling point increases with how the boiling point and melting point increases with increasing number of carbons. You see? Direct relationship. Alkanes are insoluble in water but soluble in non-polar organic solvents, of course. Because alkanes are generally less dense than water, they float on its surface. Low molecular weight alkanes are volatile and must be handled with care because their vapors are flammable. Mixtures of alkane vapors and air can explode when ignited by a single spark. Mineral oil, petroleum jelly, paraffin wax are mixtures of higher alkanes. All are harmless to body tissue and are used in numerous food and medical applications. Properties of alkanes: odorless or mild odor, colorless, tasteless, non-toxic, non-polar, insoluble in water, but soluble in non-polar organic solvent, less dense than water, so they float on water, flammable, otherwise not very reactive. So let's stop at this point and continue next